From high school, we have some familiarity with graphs. In 2.2, we talked about graphs and the relationship between the graph and function and how to kind of bounce back and forth between the two. In 2.3, we're going to talk about properties of functions. So how can you talk about a function and describe it to somebody and have it make sense? First definition, a function is called even if for every number x in the domain, if you did f of negative x, you get f of x back. So one thing to note is that if x is in the domain, for this definition, to even make sense, we need to have negative x in the domain as well. So if f is even, then it has a symmetric domain. Right. Whatever you get rid of in terms of positive numbers, you also have to get rid of negative numbers or their corresponding negatives for it to be a symmetric domain. Now that is just a property of f being an even function. If a function has a symmetric domain, does not mean that it's even. It's just that if it's even, it has a symmetric domain. So the prototype that we're going to look at is f of x equals x squared. Right? You can plot these however you feel comfortable with. So 3. Right. We're going to see in the next section quick ways of graphing these types of functions. But since this is our prototype, notice, right, if you take f of negative x, you get negative x squared. And if you did negative x times negative x, and you shuffled things around using the commutative property of multiplication, you get the two negatives next to each other, which knock each other out. Then you have x times x, which is x squared. And so that's how that definition works algebraically. But notice a function is even if and only if. Again, that means that what I have written over here is equivalent to this next statement. So if its graph is symmetric, there's that word again, with respect to the y-axis. So if you only knew what was happening in the positive direction, you can just fold your graph over the y-axis and trace it to give you the full graph. So if we have even functions, the next type of function we have is odd, and that's if for every number x in the domain, f of negative x is equal to negative of f of x. That negative comes out front, and this note right here, it's the same note as for even functions. Again, because if you have x in the domain and you're looking to plug negative x into the function, that means that negative x is also in the domain. So the domain has to be symmetric for an odd function. Our prototype is x cubed. And there's not enough space here, but this thing looks kind of like a sideways S backwards. I don't know how you want to describe it, but that's the graph for f of x equals x cubed. And let's see the algebraic side of things. We'll just talk about that. So that cubed is really negative x times negative x times negative x. You have three negative things multiplied together, which means the outcome is negative. Then you have x times x times x, which is x cubed. And this is really just negative of f of x. So a function is odd if and only if its graph is, again, symmetric with respect to, and this is going to sound kind of weird, but with respect to the origin. And what that means is if you take this graph right here and fixing the origin, you spin the graph 180 degrees around, the picture doesn't change. So, i.e., rotating the graph 180 degrees around the origin doesn't change the graph. What we're going to do is check out algebraic ways of checking this. So for any of these, when you want to determine if a function is even, odd, or neither, which just means it doesn't have this nice kind of symmetry, all you do is take negative x and plug it in to your function. If we do that, again, negative x quantity squared is the same thing as x squared minus 5. That was the original function f of x. So f of negative x is equal to f of x, which means that this is an even function. So if we were to graph this function on a graphing calculator, it should be symmetric about the y-axis. And just a quick graph on my phone. See how if I was to fold my screen in half, the left side would sit directly on top of the right side with that blue curve. Next, we'll try out this function. You have f of negative x cubed minus then negative x. So like we saw up here, if you have negative x quantity cubed, there's a negative that pops out, and you're left with x cubed. Then you have minus negative x, which gives you positive x here, which this is not our function g of x. But if we were to take a negative out of both of these, well, there's g of x. So this is really just negative of g of x. All right, and you may ask yourself, how did I know to take the negative out? This number 5 changed signs, and this number in front of the x, which was a -1, also changed signs to a +1. So there was an extra negative floating around in both of those. Since g of negative x is equal to negative g of x, this gives you an odd function. And if you want to see the graph of that, let's do 5x cubed minus x. All right, you get this kind of shape here. And if we zoom in just a little bit, right, still symmetric. So if I rotated my phone around 180 degrees, looks exactly the same. All right. Try out this next one. All right, all we're going to do is plug in negative x. We know what happens with the negative x quantity cubed. That becomes negative x cubed minus 1. Only one of the terms changed. That -1 stayed the same. So this is not equal to h of x, right? Because there's a negative here. But because there's a negative here and this did not turn positive, we know that h of negative x is also not equal to negative h of x, right? Because that negative here would change both signs, and only one changed, which means that this function is neither even nor odd. All right, and if we want to check out to see what that looks like, we have x cubed minus 1. And we have this. So notice that if I spun this around 180 degrees and lined up the x-axis so it matched exactly where it was before, this now is above that line whereas it was below that line. It's not symmetric. Let's play around with this function a little bit. What's the domain for big F of x? We know that x plus 1 cannot equal 0, which means that x is not equal to -1. And I claim that this function has no symmetry right away. The domain is -infinity to -1, -1 to infinity. And if you were to draw that out on a number line, and here's the number 0, right? This point is missing. So this side to the left has one fewer points than the sides on the right. If this was perfectly balanced at 0 before we removed that point, by removing that point, it's no longer balanced. So right away, because the domain is not symmetric, we know that this is neither even nor odd. And to see a graph of that, we have 1 divided by... Right, and so that thing is shifted. Right. If we were to fold it over the vertical line, it wouldn't be the same exact graph. And if we took this and we rotated it right around the origin, it would also give us a different graph. So this thing has no symmetry. Lastly, we want to check out the absolute value function. Recall that the absolute value function is defined to be x if x is positive, or sorry, non-negative, and negative x if x is negative. So if we plugged in negative x, well, one property of the absolute value function is that it splits up over multiplication. So this trick right here was using the fact that negative x is equal to -1 times x. And then you can break up the absolute value over multiplication. And the absolute value of -1 is 1. So this just gives us absolute value of x, which gives us g of x. And so this function is even. And if you were to graph the absolute value function, it's that V shape. And so if you folded it over the y-axis, you end up getting the same exact shape.